Good evening, everyone. Let's just wait for 5 minutes so that everyone can join. Today we'll be solving some wave equations. So basically, wait a second. We'll be solving wave equations corresponding to the strings for two cases. For one case when string is attached from both the sides. For example, 0 to L. L L is the length of the string and it is attached on both sides. In that case, we'll be using the method of separation of variables to solve the equation. And also we will look at some questions where the string is of infinite length. So when we have infinite string. So we'll be solving questions related to these two cases. Okay. So let's start with the first question. Find the solution of the initial value problem. You know, we all know that the wave equation is given as utt minus c square uxx is equal to 0. And here in this case we have 0 less than equal to x less than equal to L. That means the string is attached on both this. String is of finite length. Then we have t positive, time t represents the time. Along with that, we have some conditions. U at 0 t is equal to 0. Ut u at 0 t is 0. That means it is attached. The string is attached on one side. Ut at lt is equal to 0. That means the displacement at point L is 0 for every t. Then we have ux0 is equal to a sine pi x by L. That means at time t equals to 0, the string is following the path of this function a sine pi x by L. And ut x0 is 0. That means at time t equals to 0, the string is stationary. So if you want to see how it looks like, so initially we have a string of length, finite length, 0 to L. So at time t equals to 0, it is something of the form like this. At L equals to 0, yes. So at time t equals to 0, the string is, we can say, displaced a little bit, and the shape of the string is same as the curve of this function at time t equals to 0. Then okay, this and the and at time t equals to 0, it is stationary, so it is not moving initially. This tells us this part. And utlt equals to 0 tells us that the vibration had stopped, at this point. That means from here also it is stationary. This tells us that here also the movement is 0. And this, okay, so all those things are not necessary for us. All we need to do is solve it. So we'll be using the method of separation of variables to solve this problem. Let me mark it as equation 1. Solution. We will be using the method of separation of variables. That means we will assume, that is, we will take uxt is product of some function x and t, where x depends completely on x and t depends completely on t, so that we can make the problem into separation of variable type. Now this gives us that utt is equal to x at x and t double dash, because x is independent of t, so derivative of x with respect to t will give us nothing, just a constant. Similarly, we will have uxx is equal to x double dash x t, because again t is independent of x. Now putting this in our equation, we get this implies 0 is equal to utt minus c square uxx is equal to xx t double dash t minus c square x double dash x t t. Now this gives us x double dash x by x x is equal to t double dash t by c square t. Now see, the left hand side is a function depending completely on x, and right hand side is a function that depends completely on t, and at the same time they both are equal. So this can be possible only if they both are equal to some constant. We'll take that constant to be lambda. So let's mark this as 2. Also, we had some initial conditions. So since 0 is equal to u at 0 comma t. Now what is u at 0 comma t? It is x at 0, t at t. For every t positive, this implies x at 0 must be 0, because this is a function, this is a constant, and the product is equal to 0. That gives us that x 0 must be 0, because if was a trivial 0 function, in that case our function uxt will turn out to be a trivial solution. That is not what we want. We want a non-trivial solution, so that we get something. We don't want trivial solution. So that gives us x at 0 is equal to 0. The other condition was ut at l comma t. Now derivative of u with respect to t at point L comma t gives us x at L t dash at t, because again t is independent of x, so differentiating it with respect to t will give us this. Now let us assume that t is not constant. We'll deal with it later. Suppose tt is not a constant. That is, t dash t is non-zero. In that case, we get x is 0. We will be using these two conditions, boundary conditions. So by equation second, we have we have x double dash is equal to lambda x, along with the boundary condition x0 equals to 0 is equal to xl. So this is a Sturm-Liouville problem. If you remember, we had solved such problems, a lot of such problems, and we all know how to solve it. We will be taking different possibilities of lambda, and then we'll get some a sequence of eigen values lambda n, and for that we'll get a sequence of eigen functions xn, that will give us the non-trivial solution. So let's do that again. So the auxiliary equation corresponding to this equation, auxiliary equation is r square minus lambda is equal to 0. R square is equal to lambda. So we'll have case 1 when lambda is equal to 0. In this case, we'll get r is equal to 0, 0. That means xx is equal to c1 plus c2x. Now we had 0 is equal to x at 0, which is c1. This gives us that x is just c2x, and 0 is equal to x at L, which is c2L. Now, since L is non-zero, obviously if L is 0, then the length of string is 0, and that's uh, nonsense. So this gives us C2 is 0, therefore x is trivially 0. Now if x is 0, this gives us that uxt is also a trivial solution. That is not what we wanted. So we'll go to case 2. Case 2, when lambda is positive. In this case, we'll take lambda to be square of some function for some k non-zero. So here we have r is equal to plus minus k, and xx is equal to c1 e to the power kx plus c2 e to the power minus kx. Now we have the boundary conditions. 0 is equal to x at 0, which is c1 plus c2. This gives us c2 is equal to minus c1. This gives us xx is equal to, putting c2 equals to c1 and taking c2 equals to minus c1 and taking out c1 as constant, taking out c1, we get c1 times e to the power kx minus e to the power minus kx. Now also we have another boundary condition, xl. X at L is also equal to 0, which is c1 e to the power kl minus e to the power minus kl. This gives us that c1 must be 0 because e to the power 2kl is never 0. This implies e to the power kl is never equal to e to the power minus. Now since c1 is 0, from this equation we have c2 is equal to 0, and hence x is 0, which implies again our solution is a trivial solution. That is not what we wanted. So now we'll go look at the third case when lambda is negative. So let's see what happens for the case lambda negative. We hope that we get a solution, otherwise we are left with just a trivial solution. So we have case 3 when lambda is negative. So here we'll take lambda to be equal to minus k square for some k non-zero. Now this gives us r, which is r square equals to lambda is minus k square. This gives us r is equal to plus minus k iota. And we know that in this case, our solution x is given by c1 cos kx plus c2 sin kx. Now again using the boundary conditions, we have 0 is equal to x at 0, which is c1. This implies our function x is just c2 sin kx. Also, we have another boundary condition. 0 is equal to x at L, which is equal to c2 sin kl. Now we want a non-trivial solution. That means C2 must be non-zero. Now, for C2 non-zero, we must have sin KL equals to 0. We must have KL sin KL is equal to 0. That is, KL should be equal to n pi, or K, instead of K we'll write Kn because it is depending on n, is equal to n pi by n. So this gives us lambda n equals to minus n square pi square by L square. And for all such lambda n, we have a solution xn x, which is equal to some Cn. Again, constant is also depending on n, sine k, or instead of k we can write n pi by L times x. So this is our xn. Now we will find Tn. In this case also only, because for the above two cases, for lambda equals to 0 and lambda negative, we already got that uxt is 0. For lambda negative, we got some x. Now we need to find t. Now by equation 2, we know that, we can see that from equation 2 we have t double dash is equal to lambda c square t. So we get t double dash minus lambda c square t is equal to 0. Now for lambda negative and 0, for lambda negative and 0 we already, lambda positive and 0 we have already seen that there is no solution. The solution might exist only if lambda is equal to lambda n. So we will replace this lambda n, and for corresponding to lambda n we will try to find the function Tn. So our auxiliary equation in this equation is given by, auxiliary equation is r square minus lambda n c square is equal to 0, which is r square is equal to lambda n c square. And what is lambda n? We have seen that lambda n is equal to, see, minus n pi by L whole square. So this is minus n pi c by L whole square. So that means r is equal to plus minus n pi c by L iota. In this case, we know that the solution Tn will be given by some an cos n pi c by Lt plus bn sin n pi c by Lt. Now, after this, we need the boundary condition or some condition on t. So we already had a condition. So out of the four initial conditions given, we had used just u0t and ut at lt. We can use this one. So from here, we have tn dash t is equal to an n pi c by L minus sin n pi c by Lt plus n pi c by L bn cos n pi c by L t. Now we are given that ut, or we can write it as zero is equal to ut at x comma 0, which gives us xx t dash 0 for every x in 0 to L. This was the initial condition that we were given in the problem itself. See, ut at x comma 0 is 0. This gives us t dash at 0 is 0. Now what is t dash at 0? This gives us 0 is equal to, or instead of, okay, let's not write it tn, let's write it t only. T dash at 0 is n pi c by L bn. This gives us that bn is 0. Therefore, tt, or we can write it as tnt because it is depending on n, is equal to an cos n pi c by L t. Now we have xn and we have tn. Now we'll be using the method of using the principle of superposition. Therefore, by the principle of superposition, we have uxt is equal to summation n from 1 to infinity xnx tnt. That is uxt is equal to summation n from 1 to infinity some other constant dn, which is just cn times an, sine n pi x by L times cos n pi c by L n pi c by L times t. So this is our solution. You can see that we till now we have used the three boundary conditions and we are left with a constant dn. We still need to find the value of this dn. Now this dn we will find this dn using the last condition that is left with us, that is, now we have a sine pi x by L is equal to u at x comma 0. Now from here u at x comma 0 is, since cos 0 is 1, this is equal to dn sine n pi x by L. From here we know that this gives us a sine pi x by L is equal to summation n from 1 to infinity dn sine n pi x by L. Now if you remember our earlier sessions where we discussed the Sturm-Liouville problems, there we have seen that this dn can be evaluated and it is given as dn is equal to integration from 0 to L fx. Here fx is a sine pi x by L times phi n x, which is sine n pi x by L by 0 to L sine square pi x by L dx. Now I would like you to evaluate this dn. Just integrate it and see what this dn comes out to be. I'll wait for 5 minutes so that you can do all your calculations and find what this dn will be, so that at the end we can have an explicit form of our solution. Now this is very easy to check that this dn is equal to a for n equals to 1. Clearly for n equals to 1 the numerator and denominator are same except for a, and it will turn out to be 0 for n not equal to 1. Therefore, the explicit form of our solution uxt is equal to a sine n pi x by l times cos n pi c by l t. Next, let's have a look of some similar questions. We'll be using the similar methods to solve this question. Question number 2. Find the solution of the initial value problem. Or we can write it as initial boundary value problem, because we have initial value as well as boundary value. Boundary value problem. UTT minus c square uxx is equal to 0 for every x belonging to 0 to L. That means our string is of finite length, t positive, with the conditions u at LT is equal to 0 is equal to u at x 0t. That means at both the ends it is tied for every t positive. U x at 0 is 0. That means at time t the string is at rest for every x in 0 to L. That means at time t it is something like this straight line. And the other next condition is ux0 utx0. That means the displacement or the movement, yes, the movement at time t equals to 0 is given by mu x L minus x for every x belonging to open interval 0 to L, because since it is tied at both the endpoints, it does not have any movement there. So again, try using the separation of variable. Take ux t to be and find out what xx should be, lambda n and corresponding t in t. I will wait for 10 minutes. Please try it yourself following the same method. Just take xx uxt as xt, then putting it in the given problem utt minus c square equals to uxx. From there you'll get two equations. On one side you will be having a function of x, on the other side a function of t, and since they both are equal they must be equal to some lambda. And then for different values of lambda, try to see where we can find the non-trivial solution. So I'll be waiting for 10 to 15 minutes. Please try it yourself. After that, surely I'll tell you the solution, but I would like you to solve it yourself first. Let's solve it. I hope after taking uxt equal to xxt, you must have got the initial conditions as x0 is equal to 0 is equal to xl from these conditions. From here, you must have got t at 0 is equal to 0, and using this condition and the fact that after putting uxt in the given equation you get that x double dash by x is equal to t double dash by c square t equals to lambda. From here you must have got that for lambda n equals to minus n square pi square l square, uh, the function xn is non-zero and x is given by, this is given by some constant cn times sine n pi x by l. And further, taking this lambda n and the equation second, you let's mark this one as first. You must have got tn t to be equal to some an times sine n pi c by l t. I hope till here it must have been easy for you, because you have to just repeat the steps that were done in first part. The only difference here is this condition. From here, our constants will vary. So now, by the principle of superposition, by the principle of superposition, we have uxt is equal to summation from 1 to infinity some other constant dn times sine n pi x by l times sine n pi c by l t. So we have the condition as ut at x comma 0 is this. Now what will be ut? This implies that ut x is equal to summation n from 1 to infinity. Let's just differentiate it with respect to t. We will get n pi c by l times dn sine n pi x by l cos, because sine n pi x by l is completely independent of t, and the derivative of sine x is cos x, so this is cos n pi c by l t. Now we have mu x l minus x is equal to ut at x comma 0, which is equal to summation n from 1 to infinity n pi c by l dn times sine n pi x by l, because cos 0 is 1. So from here we get that n pi c by l times dn can be evaluated as integration 0 to l mu x l minus x times sine n pi x by l by dx 0 to l sine square n pi x by l dx. Now let's just evaluate these integrals. Now we have 0 to l sine square n pi x by l dx is equal to 0 to l 1 minus cos 2 n pi x by l by 2 dx. You can easily integrate it, and after putting the limit you will get this is equal to L by 2, and the numerator 0 to L mu x 1 minus x sine n pi x by L. Here you will have to use repeated integration by parts. Let's try this. So from here this is mu 0 to L x minus x square sine n pi x by L dx. So now we'll be using integration by parts. That gives us mu first term as it is. Integration of sine is minus cos n pi x by L n pi L limit from 0 to L minus integration 0 to L derivative of first term 1 minus 2x. Integration of sine is minus cos n pi x by L by n pi L, which is equal to mu. Now putting x equals to L, we'll get cos n pi. Since cos n pi is minus 1 to the power n. Wait a second. This was not 1 minus x. This was L minus x. So this is Lx. Now putting x equals to L, we'll get 0. Again x equals to 0, also 0. So this is 0 plus L by n pi. Now again using integration by parts, L minus 2x as it is. Integration of cos is sine n pi x by L by n pi L 0 to L minus integration 0 to L derivative of the first term gives us minus 2. Integration of cos is sine n pi x by L by n pi L. Again here when we'll put x equals to L, we'll get sine n pi, which is 0. X equals to 0, sine 0 is 0. So this is completely 0. We are left with mu 2L square by n square pi square. Integration of sine is cos n pi x by L times L by n pi, putting limits 0 to L. Which is equal to 2 mu 2. Where does this 2 come from? X square minus 2. This is 2 mu L cube by n cube pi cube, When we put x equals to L, we are left with cos n pi. Cos n pi is minus 1 to the power n minus 1. So therefore, our constant, what was it? N pi c by L, n pi c by L dn is equal to 2 mu L cube by n cube pi cube minus 1 to the power n minus 1 upon L by 2. This is L and this is 4. So this gives us dn is equal to 4 mu L power 4. This L gets cancelled out. So just L cube by n power 4 pi power 4 c minus 1 to the power n minus 1. I would recommend you to please go through these calculations again. There might be some mistake. So this gives us our uxt is nothing but summation in from 1 to infinity this dn, and what else we had, dn times sin n pi x by L and sin n pi c by L times t, where this dn is given here. Similarly, we have the next question, question number 3. Solve the following initial boundary value problem. Utt minus c square uxx is equal to 0 for every x in 0 to L, t positive. U0t is equal to 0, which is equal to ULT. Ut at x comma 0 is 0. Ux at 0 is mu naught sine cube pi x by L. This is to solve this also you need to follow exactly the same procedure. The only difference will come when you will be finding the constant, the coefficient dn. It might differ. So in that case, uh, let's discuss this at the end. So before that, I would like to solve a problem where we have infinite length string. So let's discuss this at the end of the session. So, okay, next we have question number 4. Solve the initial boundary value problem utt is equal to c square uxx for all x positive and t positive. So in this case, the string is not of string is of infinite length, and since we can't find the boundary condition, the second boundary condition, so that means basically we have just the initial value. So in that case, we cannot use the method of separation of variables, because in that case we won't be able to eliminate some lambdas and we won't get similar scenario. So we will be using D'Alembert's method to solve this problem. So let's see what are the initial conditions given here. Ux at 0 is x for x between 0 and 1, 2 minus x for x between 1 and 2, 0 for all x greater than 2. Then we have u2 at x comma 0 is equal to 0, u0 comma t is equal to 0 for every x for every t. So we will be using a similar kind of methods that we had done in the previous lecture. There we did some substitution and converted this problem into a problem with some other variables, zeta and eta, as we did in earlier classes. So I hope you remember that. We will take zeta to be x plus ct and eta to be x minus ct. So that will give us ux is equal to u zeta plus u eta. Uxx is equal to u zeta zeta plus 2u eta zeta plus u eta eta. I hope you remember everything, how we did all these things. Uy is equal to, sorry, not y, here we have t. Ut is equal to cu zeta minus cu eta, which gives us utt is equal to c square u zeta zeta minus 2u eta zeta plus u eta eta. Now we have utt minus c square uxx is equal to 0. This implies 0 is equal to utt minus c square uxx, which is basically just u eta zeta times minus 4 c square. So which gives us u eta zeta is 0. That means del by del eta of del u by del zeta is 0. This implies the function del u by del zeta is constant with respect to the function eta. That means it is a function which does not depend on eta. That means it is a function that depends completely on zeta. So this implies del u by del zeta is some function, say f of zeta. Now integrating both the sides, we will get that u zeta eta would be some integral of u zeta, again that will be a function of zeta again. So I'll take that to be f1 zeta plus some other function that depends completely on eta, because again its derivative with respect to zeta, derivative of this with respect to zeta will be 0, and we'll go back to this equation once we differentiated it with respect to zeta. So now replacing zeta eta with x and t, this gives us uxt is equal to f1 x plus ct plus f2 x minus ct. Now let's look at the boundary conditions. So we have u at 0 t is 0. 0 is equal to u at 0 comma t, which is f1 ct plus f2 minus ct. This gives us f1 at ct is equal to minus f2 at minus ct. Okay, I'll just take this to be equal to some other function gx. We also have ut at x comma 0 is 0. Now derivative of u with respect to t gives us t times f x, putting t equals to 0, just x, and minus c times f dash at x. So this gives us f1 dash x minus f2 dash at x is equal to 0. Now this gives us we have one more condition now. U at x equals to 0 is gx. Also gx is equal to u at x, which is f1x plus f2x. From here we get f1 dash x plus f2 dash x is equal to gx. Also we have f1 dash x minus f2 dash x is equal to 0. Now from these two equations we get f1 dash x is equal to 2 times f1 dash x is equal to g dash x, which gives us f1 x is equal to gx by 2, which implies that f2 dash x is again equal to, or we can say we have some extra arbitrary constant as well, plus k1, and f2 dash is equal to f1 dash implies f2x is also equal to gx by 2 plus some other constant k2. This implies uxt is equal to, let's integrate it properly so that we know what the constants will be. So since the condition is from, since x naught the initial point is 0, we will integrate it from 0 to 2, sorry 0 to x. We get 0 to x f1 dash x dx is equal to 0 to x g dash x, which gives us 2 times f1x minus f1 at 0 is equal to gx minus g at 0. This implies f1x is equal to gx by 2 plus f10 minus g0 by 2. So this is our f1, and f2 dash x is equal to f1 dash from here, f1 dash, which is equal to g dash x by 2. Now again integrating from 0 to x, we will get f2x minus f2 at 0 is equal to gx by 2 minus g at 0 by 2. So this gives us f2x is equal to gx by 2 plus f2 at 0 minus g0 by 2. Now we haven't used this condition. From here we get that f1 at 0 is equal to minus f2 at 0. So this can be written as gx by 2 minus g0 by 2 minus f2 at 0. So now uxt, what was uxt? Uxt was at x ct plus f2 at x minus ct. This is equal to, now f1 at x is gx plus ct by 2 minus g0 by 2 minus f2 at 0 plus f2 at x minus ct is g g x minus ct by 2 plus f2 at 0 minus g0 by 2. Now this gets cancelled out. We are left with gx plus ct plus gx minus ct by 2. Also, we know that what is g? G is this function. From here, g at 0 is 0. So, this is our solution. Moreover, we can explicitly see what gx plus ct and gx minus ct will be. So, we have gx plus ct is equal to x plus ct whenever 0 is less than equal to x plus ct is less than equal to 1. Then we have it is equal to 2 minus x minus ct whenever 1 is less than equal to x plus ct is less than equal to 2, and 0 for all x plus ct less than strictly greater than 2. Now, similarly, and gx minus ct is equal to mm, let's just write it as x plus ct whenever, okay, that would be fine this much, and gx minus ct is equal to x minus ct for 0 less than equal to x minus ct less than equal to 1, 2 minus x plus ct for 1 less than equals to x minus ct less than equal to 2, 0 for x minus ct is greater than 2. If you want, you can just expand it in a more clear way and see how this uxt will look like explicitly. So the main method, the D'Alembert's method, says that uxt is of this form. I hope this solution was fine with everyone. We started with some substitution method, converted this problem into a problem with other independent variables, and using the initial boundary conditions that were given, we found the explicit form of our solution. So if you have any doubt, please let me know. Let's move to the next question. This is question number 5. A string is stretched between the fixed points 0, 0 and L, comma 0, and released at rest from the initial deflection, and released at rest from the initial deflection. By initial deflection, we means that initially the string was not a straight line. In fact, it was deflected in some way. That is same as some given curve. We'll see from the initial deflection given by fx is equal to 2kx by l for all 0 less than x less than l by 2, and 2k by l, l minus x for l by 2 less than l, x less than equal to l. Find the deflection of the string at any time t. Now here in this question, we are not explicitly given the initial conditions. In fact, we need to understand what the statement of the question says, and using that we need to find the initial condition. Clearly, we are studying the wave like motion of a string. That means we will have to solve a wave equation. So that is utt minus c square uxx is equal to 0. Now see, we are given that the string is fixed at the points. So let it be this point be 0, 0 and this point be 0, L. So the string is fixed here and here, and there is a deflection initially. Initially, the string is following some curve. It is of this form, where this straight line has the equation 2k x by L, and this has 2k L, L minus x. So initially, you can imagine that a wire is fixed at both ends, and you just stretch it from between. This is exactly L by 2. So you are just stretching it from a middle way, and this string has some shape, something like this. But initially it is at rest. So you have just kept it like this. So this gives us that u 0 comma t is equal to 0 is equal to u l comma t, because at any time t the string, the position of the string at point 0 and l is fixed. Then we have that initially it is at rest, so that gives us ut x comma 0 is 0, and u at time t equals to 0, u x equals to 0 is fx. So actually we need to solve this equation. So again, this is the same as we had been doing earlier. All we need to find is the value of lambda n such that ux, let me see. So Now again we'll take uxt to be xxtt, which gives us x double dash by x is equal to t double dash by t c square t. Since this gives us x double dash minus lambda x is equal to 0 and t double dash minus c square lambda t equals to 0. Moreover, the initial conditions gives us x at 0 is 0, which is equal to x at L. Also, since ut at x comma 0 is 0, that gives us t dash at 0 is 0. So using these conditions and the equations as done in this term Liouville problems, I want you all to solve this and just find for what values of lambda we will have non-trivial solution. I'll just wait for 5 minutes so that you can solve it. And please let me know what, just find what will be that non-trivial solution. So from here we'll get that for lambda n equals to minus n pi by L square, we have x is equal to cn times sine n pi x by L, and T will be equal to some constant an times cos n pi x by L. Sorry, not x, n by c t by L. And this will give us that uxt is equal to summation n from 1 to infinity some other constant dn sine n pi x by L cos n pi c by L times t. Now this up to this you must have done using these three conditions. So we have one more condition, ux0 is fx, that gives us fx is equal to ux0, which is equal to summation n from 1 to infinity dn. Since cos 0 is 0, sorry, cos 0 is 1, we have this is equal to this. Now from here we all know that we can evaluate these coefficients dn as integration 0 to L fx sine n pi x by L dx by 0 to L sine square n pi x by L dx. So all this is just basic integration. You can see, you can just evaluate. Again, this would be L by 2, we have done earlier also, and the above term is just a sum. You'll basically have to use integration by parts. 0 to L by 2 times you have 2k by L x sine n pi x by L plus L by 2 to L 2k L minus x by L times sine n pi x by L. This is all just basic integration. You all can do it very well. Okay, so let's move to the last question. Question number 6. The points of trisection of a string are pulled aside through a distance b on on opposite sides of the position of equilibrium, and the string is released from rest. And the string is released from rest. Derive an expression for the displacement for the displacement of the string at any subsequent time and show that the midpoint of the string is always at rest. That means the displacement at L by 2 at x equals to L by 2 is 0. So basically we need to solve the wave equation, solve the wave equation utt minus c square x is equal to 0 along with some conditions. Now let's understand what those conditions will be. So we are given that we have a string of length L. So this must be its position of equilibrium. So it says that at the point of trisection L by 3 and 2L by 3, the string is pulled a distance of B in opposite directions. So this is 2L by 3. So this is pulled by a distance of B at opposite directions. So the string is something of the form this initially. So we have u at x comma u at 0 comma t is equal to 0, which is equal to u at L comma t because it is tied at both the ends. Then initially u at x comma 0 for time t equals to 0, it its displacement can be reflected by some function f, where this f is just piecewise function with some straight lines. So if I take this to be L1, this to be L2 and this one to be L3, we can see that slope of L1 is, for L1 the slope is 3a by L. Wait a second. The slope is 3b by L. So the equation of L1 is y is equal to 3b by Lx. Similarly, you can see that equation of L2, again since slope will be, in this case the slope will be minus 6b by L, and the equation will be y is equal to 3b minus 6b by L times x. Similarly, for L3, we have slope is equal to, in this case slope will be 3b by L again, because these two are basically parallel lines, 3b by L, and its equation will be given as y is equal to minus 3b plus 3b by Lx. So this fx follows this line L1 for x belonging to 0 to L by 3. So this fx is equal to 3b by Lx for 0 less than equal to L, not Lx, x less than equal to L by 3. Then it is 3b minus 6b by L times x for L by 3 less than equal to x less than equal to 2L by 3. Then it is minus 3b plus 3b by L x for all x between 2L by 3 to L. That's it. So these are our initial conditions. Also, since initially it is at rest, we are told that the question says that the string is released from rest. That means initially the velocity is 0. That means we have ut at x comma 0 is 0. So now we'll be solving equation 1 along with boundary conditions star as we did earlier. So in this case also you'll get non-zero solution for lambda equals to minus n. Wait a second. So here we will get solution taking uxt is equal to xx tt. We will get that for lambda n equals to minus n pi by L square, we have x is equal to some constant cn times sine n pi by Lx using the same method that we had been following till now. T and t will be some other function bn times cos n pi c by L t, which gives us that uxt is equal to summation n from 1 to infinity some other constant dn sine n pi by Lx cos n pi c by L t. So till now you must have you must have used just the three initial conditions. So u0t, ult and ut at x0 is 0. After next we will be using the condition ux0 equals to fx. So that gives us fx is equal to ux0, which is equal to summation n from 1 to infinity dn sine n pi x by n, because cos 0 is 1. Now we need to find this dn so that we can prove that ux at L by 2 is 0. Now we can see that what is ux at L by 2? Now this is summation n from 1 to infinity dn sine n pi x by L cos n pi by 2. So we know that for when n is odd, this for even n, this will be 0 for when n is odd. So that means this should be summation k from 1 to infinity d 2k sine 2k pi x by L cos that will be cos k pi, or we can replace that by minus 1 to the power k, because cos n pi by 2 is 0 for odd n. So that means we need to show that d2k is 0 or dn is 0 whenever n is even. So let's evaluate what this dn will be. Now this dn is dn is equal to integration 0 to L fx sine n pi x by L dx by 0 to L, sorry, sine square n pi x by L dx. Clearly this denominator turns out to be L by 2. So all we need to see that what the numerator will be. Now 0 to L fx sine n pi x by L dx. Now this can be split into three parts because our fx is a piecewise function. So this is equal to I1 plus I2 plus I3, where I1 is equal to integration 0 to L by 3, 3b by Lx sine n pi x by L dx. Now using integration by parts, you can calculate it. It will turn out to be equal to minus 3bl by 3n pi, or let's just remove this 3. So this will be, I want you all to please just calculate it yourself, use the integration by parts. This will come out to be 3, not 3, this will be bl by n pi cos n pi by 3 plus 3 bl by n square pi square sine n pi by 3. Then you have I2 is equal to L by 3 to 2L by 3, that will, which is 3b minus 6b by Lx sine n pi x by L dx. Again you will have to use integration by parts, and that will give us, this is equal to minus bl by n pi cos 2n pi by 3 plus lb by n pi cos n pi by 3 minus 6bl by n square pi square sine 2n pi by 3 plus 6lb by n square pi square sine sine n pi by 3, and we have I3 is equal to 2L by 3 to L minus 3b plus 3b by Lx sine n pi x by L dx. This will be equal to Lb by n pi cos 2n pi by 3 minus 3 Lb by n square pi square sine 2n pi by 3. Now adding these three terms on here, we will get that, let's take this to be I. From here we will get that I is equal to Let's collect all the coefficients of cos n pi by 3. They are minus lb by n pi, cos n pi by 3 is plus lb by n pi. Then the coefficient of cos 2n pi by 3, so it is minus lb by n pi plus lb by n pi. Then the coefficient of sine n pi by 3 is 3bl by n square pi square plus sine n pi by 3 plus 6 lb by n square pi square plus sine 2n pi by 3 times 3bl by n square pi square. Wait a second. Minus 6 lb by n square pi square. So this gets cancelled out. We are left with 9 lb by n square pi square sine n pi by 3 minus 9 lb by n square pi square sine 2n pi by 3. We know that sine 2n pi by 3 is basically sine n pi minus n pi by 3. So that can be written as now this is equal to 9 lb by n square pi square sine n pi by 3 minus sine n pi minus n pi by 3 using the identity of sine a plus a minus b. We get that this is equal to 9 lb n square pi square sine n pi by 3 minus cos n pi times sine n pi by 3, that is minus 1 to the power n times, that this is equal to 9 lb n square pi square sine n pi by 3 minus cos n pi times sine n pi by 3, that is minus 1 to the power n times sine n pi by 3. So this is basically 9 lb by n square pi square sine n pi by 3 times 1 minus minus 1 to the power n. Now this is equal to 0 for even n. That is what we wanted. No? We wanted this to be, wait a second, no, this is so this will come out to be plus. Yes. So this is equal to 0 whenever n is odd. For odd n, this is 0. But we wanted it to be 0 for a second. Oh, I'm so sorry. We need to show that u at L by 2 comma t is 0. For at any time t, we need to show that the movement at point L by 2 is 0. So from here we need to change all this. We need to prove that. Mm, yes, we need to show that the midpoint of the string is always at rest. That means the movement at point L by 2 at any time t is 0. So from here, putting x equals to L by 2, let me just rub all these things. So this is by 2. So this will be 0 whenever n is even, because sine n pi is 0. This is so we will be left with just the odd terms. So I'll just write k equals to 1 to infinity d 2k plus 1 sine, in that case we'll have to start with 2k minus 1, 2k minus 1 pi by 2 cos, and here we have n pi c by L times t. So this will be 2k minus 1 pi c by L t. So we want to show that all the odd terms, 2k minus 1 is 0 whenever n is odd. That is what we have seen. Now this is 0, which is equal to 0 whenever n is odd, and this is equal to 18 lb sine n pi by 3 by n square pi square whenever n is even. So therefore, this gives us dn is 0 for all odd n. This implies u at L by 2 comma t is equal to 0 for every t irrespective of t. That means the string is at rest at position L by 2. I hope this solution was fine with everyone. All we had done is just solve the wave equation using method of separation of variable, and the important thing was to understand the initial condition and what the question is asking. As even I did a mistake, the question was asking that we need to show that at point L by 2, at this point L by 2, the string is at rest. So I hope today's session was fine with all of you. The questions were quite calculative. You need a lot of patience and concentration to solve these questions, but they are not that much technical. You can solve them. The basic technicalities are very easy. All you need to do is be clear enough while doing all the integrations and using the initial conditions. So thank you very much. We'll meet next Friday, 6 p.m. Hopefully, you'll uh, go through the following lecture videos, and we'll be solving some questions related to those theory. Thank you.